hopefully it will be much less lag. Because
we want to start focusing and stuff.
sorry?
We're going to start like focusing and stuff.
Okay, that's better. I don't know why we have. Oh. I guess there's no audio, so I can see what. Okay. All right. Okay. All right, guys. So we are live from the Sommers Bausch Observatory of Boulder, and we are going to start setting up the telescope. We're gonna focus the camera if it's not, and if it is, then we're just gonna look at Jupiter tonight. You're okay with Jupiter? Yeah. So here we have Spencer. Getting to a shot. Yeah. Yeah, you're not in the shot.
Is there a delay?
There you
Yeah,
go.
there's a delay. You have to use that to tell us what this is. So I have the bat note mask on. We should be good to point out something.
Sorry, what?
I have the bat note mask on, so we should be good at focus.
Oh, you already put the mask. Perfect.
Yeah.
So for purpose of focusing, it's better to use a star.
Yeah.
Oh, the moon is very out tonight.
We could probably do.
Oh yeah. Vega is the one is the go-to here in this part of the world. So Vega, I should look it up. So what we're doing here is that we're looking for a star that it's kind of bright, Vega, in order to make sure that the camera is focused. Odds are that it is, because I think nobody has used the eyepiece. Normally, the light comes through a telescope and it either goes to the eyepiece or the camera. And the focusing length of the lens is different from both. So we have to make sure that the camera is set up properly. So we come here and we take a picture every second. Of the star. That's pretty good. Oh, it is pretty good. Okay, let me show you the picture. So this is a star, and of course stars don't really look like this. The reason that you have this rays coming out of here is actually because light is being diffracted. We're using a mask for the telescope that looks like this. I don't know if you're seeing it. But the idea of this mask is that when we have moved the camera into the focal point, then these lines over here that you see are going to be equidistant to the center line. So the lines on the edges are going to be equidistant to the center line. Here we see that we're actually a little bit out of focus because here it's obvious that the line is more towards the right than towards the left. So I go and move it around.
I don't know how you focus it actually.
Let me show you. So this is the this is in and out. So basically, which direction you want to go, it just depends on what happens on the TV over there. I'm looking at the TV, right? And I want to move. You see the bottom line? I want it to move to the left.
Yes.
So it's going the other way. Yeah, it's going more to the left. I think that's good. Yeah. There you go. Next time. It's not this one. So the one with the joystick is the one that moves. One that has like a D-pad. All right, guys. So we are much better now. You see now these lines are more or less at the same distance to the center. The center line is at the same distance to the left and to the right. Now remove the. Can you? Well, it's yeah. You know, remove it from there. I think it's okay. If you can reach. So we're gonna remove the mask, and you're gonna see the difference now between having the mask on and having the mask off. There you go, and it looks much more like what we're used to from the star field. This star is very bright, and then you will see the refraction patterns because there's actually a cross on the telescope holding the mirrors, one of the mirrors, and then that's why you see this cross here. Okay. Now we have focus camera, and we're gonna go into watching Saturn. So let's stop this. Oh, sorry. Sorry, not Saturn. We're looking at Jupiter. What's Jupiter's ghost? What the heck is this? Well, it seems like a galaxy, but it's
Oh, we're doing the nebula.
is it a nebula?
Yeah, it's a planetary nebula, I think.
I guess that's what. Yeah, no, I'm just. It's not even on. You can't even see it right now. I didn't know what it was. Okay, Jupiter, just Jupiter. Okay, so let's go to Jupiter. Wait, it's not saying that it's a star, right?
No, I think yeah.
Yeah, let's go. So Jupiter is very close to this line here is basically the horizon of the telescope, which is actually limited by the flat irons. I think is it limited by flat irons? Yeah. So I mean it's a little bit higher than the flat irons, but basically if you see outside right now, you see that Jupiter is kind of already setting, and hence we won't be able to see it for too long. So let's take a picture. The thing about Jupiter is that it is very bright, and you have to make sure that you have the minimal exposure.
Yeah.
I guess the minimal exposure is 0. And then the filter, yeah, the start. That's saturated, yes. So this is weird.
Looks like the pixels.
Yeah, but it's a back pixel that it's like in this shape.
Yeah, that's really weird.
But anyway, the thing is saturated, which means the source is too bright. So maybe that's part of this issue here. So the way we stop. I used the wrong thing. Oh, I mean the putting a lot. Well, the way we solve this issue is by putting a filter. And you maybe think, oh, you already have, yeah, it's the same thing. You already have the filter. Well, yeah. By the way, these are moons.
Yeah.
And yeah, we already have a filter, but this filter is not filtering enough. So let's see. U is ultraviolet, green, right? U is ultraviolet. Yes. Also, this bandpass is very small, so it's probably a good one. Green, red, and infrared. I will. Let's try green first. Yeah, I mean, H alpha is red, right? So we were there already. Basically. I mean, H alpha is probably what?
H alpha is super narrow.
Yeah, exactly. It's probably more narrow. But let's try with green. I don't know how narrow it's obviously not just the line, right?
Yeah, it's like a couple nanometers.
So let's see, take photo. Still oversaturated, and we still have this weird thing over here. Okay, let's try H alpha.
Euro 3 is blue and Euroband. That probably would work better.
See, O3 would probably work right, but I want to see how H alpha looks like now. So H alpha is a transition line, an emission line in hydrogen. Okay, so atoms emit a certain colors, a certain wavelength. And H alpha is one of the colors that hydrogen emits in the visible range of light. Because we're just looking at a very specific wavelength, then everything else should be filtered out, and then we should have a less intense image. Still saturating. Yeah, but it's way better.
It's not exploded pixels.
What?
It's not exploded.
Yeah, you don't have the weird thing going on. This is an interesting effect on the camera, why that was happening, you know. So this is still not filtering enough. Let's use, so H beta is like H alpha, but it's in the blue. Is that true? Yeah, that's true. Where's the sodium? No, I think H beta is in the blue. Is H beta in the blue?
I don't know about H beta. I never used that filter before.
I mean, just the transition line. Let me look up where H beta is. Actually, we have a H beta line. Yeah. Yeah, it's the blue. Just so H beta is actually a good line to look through. I don't remember having this filter. I think this is a new filter. All right. Take picture. Now it's pretty good actually. It's 50 counts, 50K. The maximum is 65, and if you reach the maximum, then basically everything that is at the maximum or surpasses the maximum just defaults to being 65K in terms of counts. These are counts, photon counts in a way. Well, they're probably data units, so it's something that depends on the counts of photons directly. The important thing to know here is that if you have reached the maximum, if you have saturated the camera, then you're going to lose a lot of contrast because all the very bright pixels are going to all go to the same value. Here, though, this is pretty good because you have the contrast. And then to see a contrast, you have to use another scale for. Well, this is a pretty good one. Like you can see. And I was looking, I was seeing, it looked to me like there was like, you could see the streams, the gas streams, but no. You can see though that it's not a dot, at least. No, I mean, it does look a little bit, it looks a little bit darker like up here.
You see like one band, maybe two.
Where's the second one? Like this?
Like right here. It's very like that might just be.
No, you see, like it may be my eyes, but this looks darker right here. And now the question is it really darker? Well, you look at the counts down here. It's 45. By the way, sorry, the counts is on the lower left of this window. Lower left, yeah, lower left of this window, you have the counts. So it's 45. If you go close to the center, it goes brighter, and if you go up, it goes dimmer. So this is our head. Yeah, it's kind of weird because it does look at that. But how is this not darker? I mean, I guess I could be even more precise. We're supposed to be here. This is 44. I guess it maybe stays at that brightness. It looks like a band. Yeah. This is a band. So we can talk about the how Saturn looks like. So we have been to Saturn. Actually, we are at Saturn right now. Not Saturn. Why am I saying Saturn Jupiter? So you guys have to see that. Jupiter. Aha. So you see, these bands are actually the gas in the atmosphere going in different directions, carrying different chemicals. That's why they have different colors. They call them jet streams. And we're looking at one of them. Probably this one, which is the thickest one, the one on the south. Well, I guess it depends when you see. The image is being flipped by a telescope. But also, Jupiter is kind of like the camera. I don't know how the camera is facing with respect to the telescope. So I wouldn't make a guess in if we're looking at the northern or the southern dark band that you see in this picture. But we're looking at one of those for sure. Notice that it's not right at the center, it's just a little bit over the center, over the equator. So yeah, for sure. Let me take another picture. Yeah, this one. Let me take another one. So the reason there's a difference in all the pictures we're taking is because the atmosphere is moving around, and the air of the atmosphere moves the light that's coming from Jupiter. And what I'm trying to do here by taking a lot of pictures is to get lucky and get a better resolution, because it can happen that at the moment I take the picture, the sky, like the air is just stays still, of the atmosphere stays still for that 0.1 seconds. And if that happens, then I'm going to get a better picture. And people do this in amateur astronomy and astrophotography. They take a bunch of pictures, and not only do they look at the best one that has the less seeing. That's how this effect is called. But also they stack them. They can also stack them up and do some very like coarse data processing to get a very good picture. And you see people that one had it. Like here I see it, right? Yeah. So that's for sure a thing. It's not a feature of the seeing or anything, but I actually think the first picture we had was the best one. That's a good one. is live stack? This is a new feed. I don't remember this. What did I do? Start.
Give it 1 second.
Wow. I like this. Wait, what's gonna happen here? Wait, we couldn't do 0.0001, could we?
I'm not sure.
Filter is U. That's kind of weird. I thought we were in H beta. I'm already suspicious of this weird mode. I don't know if we're set up. Let's do it. Let's see what happens.
No, not enough stars found. There must be some tracking here.
What did he say? Did he say something? Not enough stars found. Terminated.
I think it's the tracking.
How many stars do you want? Wait, we're gonna play. I'm interested on this thing. What is this? What is this thing? What the heck? This is too much technology for me. I'll play with this later. Okay. Do you know what this is? Like,
It looks like something you would do for tracking, but I'm not sure.
what you mean?
Like if you're doing
Like proper
guiding.
motion?
Yeah, like if you're doing star guiding, so that you don't have, like if you don't have good enough of a mount, so that you can make sure you're following the motion of the stars.
Like it's a way to make sure that the mount is working.
Pretty much. Like if it's not perfectly aligned with the North Pole, you would want to have it really offset with tags.
Live stack. I think it's not just calibration of the tracking system. I think, I mean, what I heard stack, I was very excited about stacking all these Jupiter pictures. Right? Probably that's something I could be able to do.
If it's stacking, then it probably just needs stars to do the astrometry.
And maybe somebody on the chat. Sorry, we haven't been checking the chat, guys. Okay, nobody's saying anything. So anyway, if anyone knows what live stack is, this is a
live stack probably means it needs stars that determine the position of your image. Like it can, so that way it can align everything. That might be what it's doing.
Is it like? But I mean, it's still a calibration thing. You mean?
Like when you're stacking, you don't just stack pixel by pixel. You stack by using your stars to determine how to align your frames. So that way you don't like get a super.
So that's why I say it's not enough stars. There's not enough stars. I mean, there's no stars, honestly.
Yeah.
I mean, well, this is here.
If you had something like a galaxy, you could probably do live stacking.
Yeah. We'll try this out. But okay, so here you also see the moons. So let me take another picture. Let me take another one. This is a good one. Yeah, so for sure here there's some type of, we're looking at the band. We changed, did the filter change? H beta. Yeah. Maybe we were in, no, we weren't in EU. Because now we're getting significantly less brightness. Maybe just because Jupiter is lower. Take another one. Sorry, we were in 50 before. Oh, it was still moving. Looks very weird. Is it still moving? Okay, I mean, this is obviously leaking off, but it looks very weird. And it makes me feel, because normally the camera is for sure rotated, because normally leaking happens down. Like the readout of the CD happens at the bottom. super interesting. Okay. Well, you know, Fabio once told me a secret. I don't know if this is still true. Ray told me that U was no filter, or the clear filter. I don't know if this is still true. Oh, okay. Go on, connect. Oh, sorry. Forward. Yeah, this is pretty good. Let's take another one. Let's take another one. It's kind of weird because, okay, here you see something, right?
You can sort of see it.
Yeah. All right. So, do you know about this jet streams? The streams from Jupiter? Just know it's very complicated fluid dynamics. Well, what more can you tell us, Spencer? I'm gonna have to Google it because I'm at a loss, and I feel like I want to say more about these things that we're looking at. Not the temperature of the zone. I mean, that's what I said. It's probably a little bit. The upper ammonia clouds visible at Jupiter's surface are organized. I don't know if you guys can read this. Um, so the upper ammonia clouds visible. So the chemicals that I was talking about are ammonia. I'm guessing that's just the darkest clouds are made out of that. And they're bounded by powerful winds that are called jets, right? And they go in opposite directions, the light and the dark ones. Okay, and also yeah, I think it is well understood. I mean, I've seen very detailed models of that can reproduce more or less what's going on. Surely is very complicated and turbulent, right? So it's very hard to have a model that actually gets all the features that we see at the same time. But I think we have a more or less understanding of why you see the different flows. So one of the things that is interesting is that one of the clouds are going out and one is going in, and also one is going westward and one is going eastward. And that also corresponds with different temperatures. One is cold and the other one is hot. And then that will also, because of the temperature, will correspond to a different chemical environment. And then one things will dissociate in one clouds, and then the other ones, so other things will form. And that's why we have the different colors. Okay. Sorry. Is there anything particularly in astronomy that you like, Spencer?
Maybe a deep space object would be cool to do.
Sorry?
Maybe it's a deep space object would be cool.
I mean, we're gonna go to the moons next, but I just want to know what you're interested in the most and what you know about the most.
Listeners said there's been like exoplanets. So That's something you can really image with telescope.
I mean, but exoplanets, a lot of them are hot Jupiters.
Yeah.
So in what way are they similar to Jupiter?
Pretty much the only way that hot Jupiters are similar to the one in our solar system is their size and mass. However, hot Jupiters are actually planets that are really close to their star. Um, they orbit their star every 10 days or less, and so they're even closer than Mercury is.
Yes, very close.
So because of that, you have these giant planets that are just superheated, and as a consequence, they're really puffy because they're so hot. Their density is really low, and they get really inflated. And they're kind of a mystery because they're really common in a lot of systems we observe, yet they aren't in our solar system, and we have absolutely no idea how they form.
I mean, I think that's the true mystery. I think that the commonality is a bias from the fact that, so the way we detect exoplanets has to do with the fractional area of the planet to the star. So how big does a planet look? How big is the shadow that the planet casts on the star? And of course, um, if you have a planet that is very big and very close, that's going to be the strongest signal you're going to get.
Yeah, it's amazing.
Another method we use to detect exoplanets is by looking at the gravitational effect that the planet has on the star. If a planet can move the star around, then we're going to see the light is going to be Doppler shifted. So that means that lines. So for example, the H alpha line from that star is going to look redder than it should be. That's because the um, the star is moving away, right? So let's see if we can find a good redshift. Amazon redshift is it's.
I do like radial velocity curve.
Wait. Redshift light. Oh, yeah, that's what I meant. This is pretty much it, right? So, oh look, of course, I very trusted Wikipedia. So, if the star is moving away, it's gonna look redder, and if it's moving towards you, it's gonna look blue. And this is a red shifted spectrum. This is what you will see from a star that is not moving. These lines over here, and then when it moves, you actually see them a little bit redder, right? So I think this is actually the H alpha line in absorption. What is the sodium 1 line?
Isn't H alpha emission?
I mean, you can always also absorb because it's probably the sodium one. I don't know which line is this one, sorry. And it doesn't say. But here they're comparing the absorption lines of the sun versus the absorption lines of the galaxies, and you see that they're redshifted. And the idea is that a way that we use to detect exoplanets is by seeing how the planet moves the star around and redshifts its light. And that's only going to happen if you have a very big planet close to the star. Right? If a small planet, like the effect that the Earth has on the sun is very small. And in the motion that it causes will be undetectable. But if you have a very big planet, then you will be able to see its effects. So this method, both methods that we have that we have used to discover exoplanets, which are eclipses in real velocity curves, like that what I just showed, the redshift. Both things really favor, like the strong signals are going to be hot Jupiter. So that's why we have detected a lot of them, right?
Yeah, it is also kind of interesting too, the other ways that other exoplanet systems look so different from our solar system. Like, as you said, a lot of this could be observational bias, but there's also a whole other class of planets called super Earths, and we also call them mini Neptunes because they're kind of in between Earths and Neptunes. And they're actually the most common planet that we've detected, but it's another thing that we don't see in our solar system. So there's a whole class of planets that you don't really see. So the question is our solar system an anomaly?
And that's a good question. So is the solar system a number? I mean, I don't think we have enough stars. Sorry. Well, I think the thing is that this field is growing so fast that we do have enough to make those claims about should you expect to see a solar system like ours. The problem is that for the longest of time we cannot see a solar system like, even if they're there, we couldn't see them, like multi-planet, for example.
Yeah, it's crazy. Like just a decade ago, I mean, we only had like a couple hundred planets discovered by the transit method. But with space telescopes like Kepler and the new one is TESS, we've expanded that number to over 4,000.
I mean, Kepler is a little bit better, but even TESS, right? Like, because you want to maximize amounts of discoveries or whatever. Like, I don't know exactly what's the maximization here, but you are looking at stars only for a few hours, right?
Yeah.
And you have to see the star you have to see the star being eclipsed twice in order to detect a planet.
Yeah, for TESS, it observes a certain patch of the sky for a total of 27 days. So yeah, and it does revisit. So we end up like having a total of 60 days of observations, half of it one time, then the next half a year apart, or even 2 years apart. So it definitely is hard for us to determine those long period planets with an instrument like TESS. But in a lot of cases, this is still better than ground-based photometry. If you're looking for it from the ground, you have atmospheric effects, which make it really hard. And you can only do it during the night. You can't do it during the day, meaning you have huge gaps in your data. And so even just getting 27 days with an instrument like TESS is pretty amazing.
Something weird happened. I've just realized this. So I'm going to show you the YouTube window. So for some reason, the name of this transmission is Sommers Bausch Observatory's personal meeting room. Well, I attempted to use this one. I don't know if we are having two simultaneous transmissions.
It looks like only one person's watching.
Let's see. This is kind of weird because this is not live.
Yeah, but it says that it looks like it switched over just to a new one.
Oh, and Erica had it. Oh, yeah. I'm sorry. Erica was actually in the shot. But this is not working.
Yeah.
Yeah, I'm just gonna ignore this. I don't know how to stop it thinking that it's transmitting when it's not transmitting.
Yeah.
Okay, so that is for Jupiter. And have we detected cold Jupiters, like just regular Jupiters?
Yeah, I mean, there are definitely massive planets that are pretty far from their star.
That we have seen.
Yeah. But definitely not quite as anomalous or not as difficult to explain as a hot Jupiter in terms of planetary formation.
Now we can look at the moons. So these are 3 moons. We're missing one. These are all Galilean moons. So Galilean moons are called so because Galileo discovered them. And I'm guessing we're missing Io because this is too far away. But if we want to know which moons are which, we can.
Looks like Io's just close.
Yeah. Yeah, so we were missing Io. Io is too close, so it's almost being either occulted or it's on top of Jupiter. I won't be able to see it. Yeah, I think we won't be able to. Let me recheck that image now. Yeah. Yeah. Maybe this is no. So maybe this can be now. Okay, so we have Europa Calisto and Ganymede. What can you tell us about these moons?
Well, as far as these specific moons, I mean, they're just 3 out of many. Well, they're the ones that Galileo was first able to observe, and the first ones that we're able to see when just doing a quick image. There's something I think like 79 moons around Jupiter. That might be a wrong number, but it's definitely close to there. Um, and it's crazy how quickly we can, or how we're still discovering objects in our own solar system. I mean, just for Saturn, it was just last year that we discovered a whole bunch of moons that made Saturn the one with the most.
Yes.
So these are definitely objects that are hard to understand and that we're still searching for. But as far as these ones, what we've been able to learn from instruments that come visit the Jupiter system, even from ground-based studies, is that a lot of them are icy bodies, meaning that they could have water on them, which makes them also pretty interesting candidates for astrobiology.
Yeah, but there is one moon that is particularly interesting for astrobiology,
Yeah.
and that is Europa, which is this one. Why is it? Yeah, Europa. Yeah. Why is it so interesting? Well, because we know that Europa is close to Jupiter. These other objects, other moons, are much further away, and they have weird orbits also because they can be capture objects. Most of these moons are, but the ones that are closer to Jupiter, they form with the planet, or the formation is associated with the planet, and they are close enough that Jupiter, they interact with Jupiter and they can get heated up by Jupiter. And that's what makes this ice melt. The ice of Europa has melted closer to the core than outside. And the reason is that the heat is coming from the inside. It's coming from the friction due to the tides that this moon feels from Jupiter. And then the water, it's global, so it means that the entire between the icy crust and the core, there's an ocean. And the ice crust is actually very thick, which protects the potential life from radiation. And that is particularly good for life because you have both the heat, the water, and the protection that is normally given to us by atmospheres. In this case, it's given just by the icy crust. So it seems that the ingredients are there to have some type of life in Europa. And we actually have a mission. It's going to go and see. It's called Europa Clipper. When does it launch? (2024). You see, Europa Clipper used to be so it's going to be actually an orbiter that is there mainly to study Europa. But it used to have a probe,
Really?
and they cut that out. Yeah. I guess it's kind of risky. Like maybe the idea is that you want to first study Europa and the surface and like know where you're gonna land.
Yeah.
But come on, like it seems like a very interesting idea to go and actually land in Europa. And the other thing is that I think we were gonna land, but we didn't have the technology to actually drill.
Okay.
And then another issue, which is actually probably the biggest issue of all of them, is you have to sterilize your ship when it's going to a place that could have life, because you don't want to affect the ecosystem in that planet by bringing bacteria from Earth. And that's a tough. That's not easy. It's very hard to sterilize the machine 100%, because even if you are in a very clean lab, when you mount it on the rocket, it's going to be exposed to the atmosphere. It's going to be exposed to bacteria. Life is everywhere on Earth, and just being on the rocket is already, like, the rocket itself cannot be sterilized. So so that is an issue for, but there is though Firefly. No, it's not Firefly. There is a mission that is going to Enceladus, I think. It wasn't Dragonfly. That's the one.
Oh yeah. Okay, that's for Saturn.
Oh no, it's going to Titan. Yeah. It's for Saturn. So Titan, Titan is another planet that is not the best candidate for life, but it is a candidate that is a good one. It has a lot of carbon, because we know that it has a lot of methane. So we already actually sent a probe to Titan, but the probe took pictures. This one, it seems like it's going to take samples, or it's going to be moving around, flying. So this one obviously can move and look at different parts of Titan. But what we sent was the Huygens probe that was actually attached to the Cassini spacecraft. And the Huygens probes went and took some pictures of Titan. Huygens probe. It didn't fly around. It just landed and took some pictures. And these are pictures. These are the pictures, actual pictures taken by this spacecraft. And you see valleys and mountains, and so that means that there's active geology in this planet caused by what I just said, the interaction with Saturn. But also there's weather, and there's a very thick atmosphere, and there's rain, not water but methane. The thing is that water is an ingredient, and we think that maybe water in Titan, but another important ingredient for life is carbon. Methane is it's made by CH4, so it has hydrogen and carbon. So that means that there's a lot of the main ingredients here as well. And we're going there. So and you know what? It is true that Enceladus and Europa may be very candidates, but the thing about Titan is that it has a very thick atmosphere, and that means that you don't have to solve the problem of drilling through the ice. Like because the drilling through the ice problem is I don't think we can actually, right now with the technology we have, we can have something that drills through the ice and because of other water. And the ice caps are interesting, but then you can make the argument that actually Titan is more interesting than the ice caps themselves. And also you can make the argument that you can just send a flyby mission to the ice caps and an orbiter, and then maybe later you can send the probe. I accidentally closed this. Okay, now it seems like things are working better. And now finally, we talk about Europa, we talk about Titan. What can you say
Turns
about?
around Saturn, so that's not fair.
I'm sorry. We talk about Europa, Ganymede, and Callisto. We have to talk about Ganymede and Callisto.
Okay.
So Ganymede is the biggest one, and I think this one is Ganymede. Let's see. Yeah. And the interesting thing about Ganymede, well, I mean, this is maybe not, has that to do with astronomy. Well, it does. Like, it's big enough that the gravitational field, what is the gravity on Ganymede? Wow, it's still very low.
Yeah.
What about Europa? Oh, sorry, you're not seeing this. So this is the gravity on Ganymede.
For reference, on Earth, it's about 9.8 meters per second squared.
And this has to be because of the proximity with Jupiter, right? This is so it's higher. Okay, so I don't know much about Ganymede. Do you know about Ganymede?
Not too much.
And I don't know about Callisto either. So let's see, Ganymede.
Well, that's crazy. It's larger than Mercury in volume.
Yeah, but it's only half that massive.
Yeah, so it's a lot less dense.
Yeah, which makes sense because Mercury. It makes sense that Mercury is very dense.
Yeah.
So Mercury, as you guys know, is the closest planet to the sun. And the only thing going around there to accrete to Mercury were rocks in the moment of formation. Well, things where Jupiter was, there was also ice, not only rocks. And ice is less dense than a lot of rocks, not a lot of rocks. That will explain why Mercury has more density. But it's not that dramatically like bigger than the other things, the other moons. So this is the thing. There's this sci-fi novel series, and now it's also a TV series. It's called The Expanse. In The Expanse, there's a community outside in the outer solar system called the Belters because they live on the main belt. But they have theorized in this science fiction novel that surely being born at low gravity is bad for you as a human being when you're growing. It affects the density of your muscles. It's not the healthiest thing to do. We are made to be born in environments that have 1G, or in this case, in terms of 9.8 meters per second squared. So the people in the belt go and actually give birth, like they go to Ganymede to give birth, so that their kids are healthy because they're growing in a more gravitational environment. For sure, like the belt has like stations in Ceres, in the actual belt. Ceres is a I guess it's a dwarf planet now. I was gonna say it's a very big asteroid. But look, the gravity is much lower than in Ganymede. So people in this novel go to Ganymede to give birth to their kids so their kids are healthy and have thicker bones. I think that makes sense. The thing is that we saw the other moons. And the other, why not go to this other moon? It's very similar.
Yeah.
Right? Io I understand why not go to Io, because Io is very close to Jupiter, so the tidal forces are even stronger. That's why the gravity is even stronger than Ganymede. And it has a lot of volcanic activity because of this. It has a lot of this yellowish is sulfur. So that's why you wouldn't want to give birth in Io, but I think that Callisto is okay. But they all go to Ganymede. I'm pretty sure that's better explained in the books. But I guess, like, if you are limited to the outer solar system, that will be a good place to have kids. Here's what we're about the hour mark. And then, yeah, the last moon here is, sorry, Callisto. We're talking about Callisto. Let's go do the NASA page, I think. In depth. Yeah, this is my perception, but both of Ganymede and Callisto, they are like boring. She's a hunk of broken ice, you know. Let's look at Io. We see a lot about Io, and we see a lot about Europa mentioned because they're more attractive apparently than Callisto. And then the only thing that Callisto does is that there's some dynamical features that are very interesting, because all these four orbits are in interesting resonance. Like, there's a 1, 2, 4, but I don't know. I remember which one. Galilean moon resonances. Yeah. So Callisto is the one that is outside of. So the first three Galilean moons are in this interesting resonance that you can see here, which is that no. Let's see. So what a resonance is that you see that every now and then the moons are going to align. Look at these three moons. And what the resonance is that every time Io does an orbit, Europa does 2 orbits, and Ganymede does 4 orbits, right? And this is a very stable configuration, so the system tends to do this type of configurations. Resonances are actually can be very stable. They can be a destabilizing force as well. But in blind formation, we see that things like to form around resonances, and that has to do also because we think, and this is theoretical, that a resonance can also drive planet formation. Like if you have another thing resonating with a near thing, it will be at the resonant points where you're going to have planets. But the interesting thing is the Callisto is not in this arrangement. In there are, but there is also an exchange of energy, I'm pretty sure. So this is the thing about the stability of this system. It was very close, and it's exchanging a lot of energy, and there's a lot of loss of energy because there's a lot of volcanoes, there's a lot of friction between Io and Jupiter. that makes it so that EO wants to actually go far. The EO wants to move far away from, it wants to recede its orbit. And Ganymede and Callisto have the role of kind of keeping this together. And I think that at the end of the day, the angular momentum, like there is a resonance, there is a place where there's a point where Ganymede is kind of like absorbs this angular momentum via the resonances, and Ganymede starts fading away. And then there's an interaction with Callisto that makes it to stay inside of this coordinated dance. So Callisto has an important role in this dance as well. And these are the 4 moons. We didn't see Io. We talked a little about it. We didn't see it. So Ganymede is the biggest one. Europa is the one that has a lot of water. And Callisto is the one that is not part of the resonance. And is the one that is further up. I think that's a good way to remember that. And I think that's all for tonight. So see you guys in 2 weeks. I'm not going to be here, but Marcel is going to be here. And I think we're going to be doing these space objects, by the way. If you want to come to that event. Because we already exhausted the planets and the moon. We did a lot of Mars last week. That was pretty good because we had Erin here. Really? And yeah, Erin is our Mars scientist. So next week, probably the space objects, okay? All right, guys.